Jai Hind everyone. This is Naresh Kumar from Ajay Kumar Garg Engineering College, Ghaziabad. Welcome to the class of Optical Communication. In the Unit 1, today we will discuss Optical Spectral Band with the operating windows and the basic concepts related to ray theory. So, for today's lecture, first topic is Optical Spectral Band and operating windows. Basically, we know that in the optical communication system, information is carried in the form of light. That is, basically we use light as a carrier signal for the modulation process. So, in the optical communication system, we require light source or light for generating the carrier signal. Okay, now this light is used as a carrier signal, must be operating with a frequency. The carrier signal frequency lies in the range 10 raised to power 13 to 10 raised to power 16 hertz. That is approximately, we can say, for example, let's say we are using the carrier frequency using light as 10 raised to power 14 hertz. Basically, we have studied that the optical communication system is a highly wavelength dependent system. That is, the performance of the optical communication system depends upon the operating wavelength selected for the operation. So, along with the frequency, optical fiber communication system can also be described through the operating wavelength range. So, for the optical communication, the operating wavelength range is basically it is 0.8 micrometer to 1.7 micrometer. That is, it lies in the range 800 nanometer to 1700 nanometer. This range of operating wavelength for the optical communication is designated as optical spectral band. So, whenever we are performing the optical communication, the operating wavelength is selected out of this range, and this range is known as the optical spectral band. Basically, we know that in the world there are a number of signals and every signal has frequency or wavelength. So, if we draw or plot a graph for all those signals in relation to the wavelength or frequency, then all those signals can be summarized in the form of a graph. That graph is known as the electromagnetic spectrum or the EM spectrum. So, all the signals lie in this spectral band. So, in this entire spectrum band, we can see that there are number of frequencies or wavelengths like long waves, radio frequencies, short wave, ultra high frequency, millimeter wave, infrared, visible region, ultraviolet, X-rays, gamma ray and cosmic ray. So, this is the complete entire electromagnetic spectrum band. Now, out of this band, what is the range that has been selected for the optical communication operation? So, that range is basically the optical spectral band, and we basically operate in this region 0.8 micrometer to 1.7 micrometer, that is between 800 nanometer to 1700 nanometer. So, this is the region selected for the optical communication in the electromagnetic spectrum. And this optical spectral band, we can see that in the spectrum, this optical spectral band lies near the infrared region and visible spectrum. So, in the EM spectrum, the optical spectral band lies near the infrared and visible region. These are the two graphs for the wavelength versus the attenuation or losses in the case of optical communication system and responsivity in the photodiode or photodetector. Basically, in the previous slide we have seen that the operating wavelength selected is, that is between 800 nanometer to 1700 nanometer. So optical communication will be performed within this wavelength range. But it is not that all wavelengths are selected for the operation. We have designated some particular wavelengths in the optical spectral band that can be used for the optical communication system. So those operating wavelengths selected are known as the windows. Okay. So in this optical spectral band, basically we operate with three windows. That is, first window that lies at 850 nanometer. We have second window that lies near 1310 nanometer, and window 3 that is operating at 1550 nanometer. So out of the entire optical spectral band, we generally deal with three windows: window 1 at 850 nanometer, window 2 at 1310 nanometer, and window 3 at 1550 nanometer. So for seeing the performance, here we have plotted the graph, and we can see that along with the change in the wavelength, or as the wavelength increases, as the operating wavelength increases, there is decrease in the losses. So we can see that the highest or maximum losses are at for the window 1, then losses are decreased further at window 2, and we have minimum losses at window 3. So losses are maximum at window 1 and minimum at window 3. And in the next few chapters we can also see that there is another phenomena along with the loss, that is known as the dispersion. That is broadening or spreading of the light pulse. So in that we will see that the dispersion in the case of single mode fiber is minimum at 1310 nanometer, that is approximately at 1.3 micrometer. Okay, so at 1.3 micrometer window 2 we will get the minimum dispersion. So we select the window, operating window, according to our requirements for the communication system. That is, whenever we have to perform the communication for a short distance, we can operate in window 1. Whenever we require minimum dispersion, we can operate at window 2, and when we require minimum losses or attenuation, we can operate at window 3. And later on we will study that the zero dispersion point available at 1.3 micrometer, this can be shifted at this point 1.55 micrometer using a particular type of single mode fiber, that is known as dispersion shifted fiber. Dispersion shifted fiber. Okay, so if we use a single mode fiber with characteristics as dispersion modified fiber, then this zero dispersion point can be easily shifted to at window 3. So in practical cases we generally prefer to operate at the higher window, that is window 3. Now the entire spectral band can be further divided into some designated sub bands used for the optical communication. That is, entire spectral band can be divided into further small bands which are designated as O band, that is original band, E band, that is extended band, short band, conventional band, that is C band, L band long band, U band, that is ultra long band. Okay, so this is the detail for all these sub bands for the optical spectral band. So next is optical fiber waveguide. Optical fiber waveguide or structure of optical fiber waveguide. Basically, optical fiber cable is used as a channel in the case of optical communication system for carrying the information in the form of light from source to the destination. So, whenever the information is carried in the form of light, we need to have a special channel that can support the propagation of signal in the form of light, and the solution is optical fiber cable. Optical fiber cable are also sometimes known as optical fiber waveguide. This is because of similarity in the structure as well as working principle. So if we compare the optical fiber cable with the conventional metallic waveguide, we can see that in the metallic waveguide, the electromagnetic wave propagates by using the principle of multiple internal reflections from the walls of the waveguide. In the similar way, as electromagnetic wave propagates in the metallic waveguide, in the similar way, optical fiber also have the propagation of light instead of electromagnetic wave, and this propagation of light is followed the principle of total internal reflection, that is light propagates due to multiple reflections from the core cladding interface. So due to the similarity in the structure and principle of operation, optical fiber cables are sometimes also known as optical fiber waveguide. So the structure of optical fiber cable is shown in this figure. Basically, the optical fiber cable has layered structure. We have the inner layer, that is known as the core, and which has a refractive index N1. Then we have a outer layer known as cladding, which has a refractive index N2. And for the propagation of light through the optical fiber cable, we ensure that always the refractive index of core is greater than the refractive index of the cladding. That is to ensure the total internal reflection, that is propagation of signal in the form of light through the optical fiber cable. During the manufacturing, we need to ensure that the refractive index of inner layer core is always greater than the cladding. And over these two layers, we can have some mesh structure, and over that we can have some plastic coating. This plastic coating is used to ensure the strength of the optical fiber cable and to avoid it from the damages, or for the protection purpose, or we can say that a protective covering layer is attached to the optical fiber. So basically here the important characteristics is, that is refractive index. Refractive index is basically the characteristics of medium or material. A refractive index can be defined as, let's say, refractive index is nothing but it is the ratio of velocity in vacuum to the velocity in specified medium. So refractive index is nothing but it is the ratio of velocity in vacuum to the velocity in the specified medium. The specified medium can be, for example, maybe air, glass or plastic. Basically the optical fiber cable is made up of glass or plastic. So out of these, the necessary condition is that the refractive index of core should be greater than the refractive index of cladding. That means this core is a denser medium. Whereas comparatively this cladding is a rare medium. So if core is a denser medium, then velocity will be less, penetration will be less, and if core is the rare medium, in that velocity of propagation will be more and penetration of signal will also be more. So this same structure will be used for propagation of light in the optical fiber system. So next is ray theory. Basically, optical communication or propagation of light in the communication system can be explained using two theories. One is ray theory, another is known as the wave theory. So here we are discussing the ray theory. Basically, in the ray theory, the propagation of light is considered by considering the ray nature of the light. Moreover, this ray theory is comparatively less accurate or approximate theory compared to the wave theory, and this ray theory is generally applied when the dimensions of the optical fiber are comparatively or sufficiently large. That is, this ray theory considers the ray nature of the light and explain the propagation of light only when the dimensions of the optical fiber are sufficiently large, and as compared to wave theory, this is less accurate, or we can say that this is an approximate theory. So under the ray theory, the first topic is total internal reflection, that is also known as the TIR. Basically, total internal reflection is the working principle of optical fiber cable. So the light inside the optical fiber cable propagates through the principle of total internal reflection. Here we explain the working principle total internal reflection. We can see that we have a denser medium glass with a refractive index N1 and a rare medium air with a refractive index N2. That is, we have considered N1 greater than N2, which is the case same as that for the optical propagation. So here we can see that there is an incident ray. We are considering light as a ray. So there is an incident ray that is incidented with an angle phi 1 in the medium 1, and so whenever this ray is incidented at an angle phi 1, basically due to the difference in refractive index, the phenomena of refraction take place. This is the normal. So whenever a ray is incidented from the denser medium to rare medium, from the denser medium to rare medium, it slightly bends away from the normal. So this ray, if there has been same refractive index, this would have traveled like this. But as there is a difference in refractive index, so refraction phenomena will take place and the ray will slightly bend away from the normal and will follow this path, or this is the exit ray. Or we can say that there will be phi 2 greater than phi 1. Let's see another case. If we keep on increasing this angle, incident angle, then this phi 2 will also keep on increasing, and there will be a critical case when this incident ray is parallel to this core cladding interface. That is, this phi 2 angle becomes 90 degree. the case when instead of refraction, reflection just starts. That critical point is basically denoted by this critical condition, critical angle phi c, and this critical angle is the minimum angle at which the ray must be incidented so that it can be reflected. So at the critical condition, reflection just starts or refraction just ends. So at critical condition we have phi 1 equal to phi c and phi 2 becomes 90 degree. So this is the critical condition. Okay, so and then if we increase phi 1 greater than phi c, this case, then instead of reflection, total reflection take place, total internal reflection take place. That is, we have incident ray as well as the exit ray or the reflected ray both in the same medium. So at the core cladding interface, the ray is reflected back and light propagates through the fiber. So in this way, total internal reflection take place and light propagates within the optical fiber cable due to multiple reflections from the core cladding interface due to total internal reflection principle. And this ray theory can be explained using the Snell's law. This Snell's law states that refractive index in one medium into sine of angle in that medium will be equal to refractive index in the second medium into sine of angle in that medium. So we can say that sine of phi 1 divided by sine of phi 2 equal to n2 by n1. And at critical condition, for critical case, we know that this phi 1 will become phi c and this phi 2 becomes 90 degree. So sine 90 is 1. So we have sine of phi c equal to n2 by n1, or we can compute the required critical angle for the total internal reflection. So we will have phi c equal to sine inverse n2 by n1. So in this way we can compute the minimum critical angle required for the total internal reflection. That is, the light must be incidented at an angle greater than this phi c, which depends upon the refractive index of the core and cladding. Only then light will propagate through the total internal reflection through the fiber. So that we have studied critical angle. It is the minimum angle. The light must be incidented greater than this angle. This derivation we have seen in the previous slide. Here we can see that the phenomena of working principle of optical fiber, total internal reflection is shown. That is, light is traveling inside the optical fiber cable with multiple reflections at the core cladding interface. Next is under ray theory. Next is acceptance angle. Okay, we have seen that light inside the optical fiber cable propagates only when the condition of total internal reflection is satisfied. Okay, so inside the optical fiber cable, the light must travel with a condition of total internal reflection. So to meet this condition of critical angle inside the optical fiber cable, it is necessary that the light from the optical source that is entering inside the optical fiber cable must make a particular angle with the axis of the fiber to ensure the condition of this phi c. This minimum angle, this angle that the light makes with the axis of the fiber, so that inside the fiber TIR can occur. This angle condition is known as the acceptance angle. That is, optical source must be placed within this angle, or the light entering inside the optical fiber cable must lie within this cone, and this cone is known as the acceptance cone. If the light entering inside the fiber is outside this angle value, that is acceptance angle or this acceptance cone, then instead of total internal reflection, light will not propagate, TIR will not occur, and light will go into the cladding, and light entered into the cladding will be eventually lost in the form of heat or radiation. So, to ensure the total internal reflection, it is necessary that the light entering into the fiber must make an angle theta A or less than theta A, so that TIR can occur. So, theta A is nothing but it is the maximum accepted angle. So, that's all for this lecture. Thank you everyone. Jai Hind.